It would take about 3 million watts of light to hold a single paperclip off a table. That is the output of a small power station, aimed at one paperclip. But it would work. Sunlight presses on your body with the weight of about 1/4 milligram. It strips dust off comets and lays it across 100 million kilometers of sky. It holds the largest stars up against their own gravity, and it has pushed asteroids thousands of kilometers off course. Which is a problem. Pushing is what momentum does, and the only formula most of us were ever given for momentum is mass times velocity. Light has no mass. 0 times anything is 0. So something inside that beam is doing a job nobody ever told you about. Tonight we find out what it is, and where, 118 years later, physics still cannot agree on the answer. Before we begin, if you enjoy watching settled physics come apart at this pace, a quick like or subscribe genuinely helps the channel along. It costs you a moment, and matters more to me than it should. Now, let's ease in. A comet does not drag its tail behind it. That single sentence contains a problem that sat in plain sight for 400 years, visible to anyone who looked up on the right night, requiring no instrument, no laboratory, and no mathematics to notice. And for most of those 400 years, nobody could explain it. Think about what a tail is supposed to do. A ribbon tied to a bicycle streams backward. Smoke from a moving train lays itself out along the track the train has already covered. A swimmer's hair trails behind the swimmer. Motion through a medium leaves a wake, and the wake points back the way you came. That is not a law of physics so much as a lifetime of quiet observation, and it settles into the mind so early that it never gets examined. A comet ignores it completely. A comet moving through the inner solar system carries its tail pointed directly away from the sun, no matter which direction the comet itself happens to be traveling. On the way in, as the comet falls toward the sun, the tail does stream behind it, and everything looks normal. Then the comet rounds the sun and starts heading back out into the dark, and the tail swings around and runs ahead of it, leading the way, pointing out toward the emptiness the comet is only just beginning to cross. For part of its journey, a comet is chasing its own tail. This is not a subtle effect. It is not something you need a telescope to resolve or a photographic plate to accumulate. Bright comets have been recorded by Babylonian scribes, by Chinese court astronomers keeping continuous records for 2,000 years, and by European chroniclers who considered them omens and wrote down what they saw with unusual care. The geometry is right there in the drawings. The tail runs along the line joining the comet to the sun, on the far side. It is worth standing under one, at least in your mind, before we go any further. You are outside on a cold, clear night, well after midnight, far enough from any town that the sky is genuinely dark. The comet is there, low and unmistakable, a soft smear with a definite direction to it. Your instinct is to look at the head, the bright, compact part, because that is where the object is. Resist that for a moment. Look at the line instead. The sun is below the horizon behind you. You know roughly where, because you watched it set. Now trace the tail with your eye, from the bright head outward, and follow that line back across the sky and down. It runs to the sun, not to where the comet came from, not along the direction the comet is moving, to the sun, and then straight out the other side. The air is very still. Nothing about the scene suggests force. There is no sound, no motion you can detect, no sense of anything being blown anywhere. The comet appears frozen, and it will still be in almost exactly the same place an hour from now. And yet what you are looking at is a plume of solid material being driven off a body of ice and rock and pushed steadily outward, and the thing doing the pushing is arriving at your own face at the same time, in the form of starlight, and you cannot feel a bit of it. Johannes Kepler wrote about it directly. In 1619 he published a small book on comets, and in it he proposed an explanation that was, given everything he had to work with, remarkable. He suggested that the material of the tail was being driven off the body of the comet by pressure from the sun's rays. Light, he thought, was pushing. He had almost nothing to support this. There was no theory of light that could produce a pressure. There was no way to test the idea, no instrument sensitive enough to detect anything of the kind, and no framework in which the suggestion could even be made quantitative. It was, in the most literal sense, a guess. But it was a guess that took the observation seriously instead of explaining it away, and it turned out to be pointing at something real. Now, because this channel would rather be accurate than tidy, there is a correction that has to be made here, and it is the kind of correction that makes the story better rather than worse. Comets do not have one tail, they have two, and the two are produced by two completely different mechanisms. If you look carefully at a photograph of a bright comet, you will usually see a narrow, straight, slightly blue feature, and a broader, softer, yellowish-white one, and the two do not point in quite the same direction. The blue one is the ion tail. It is made of gas that has been stripped of electrons by ultraviolet light from the sun, and it is being carried outward, not by light, but by the solar wind, a stream of charged particles blowing off the sun at hundreds of kilometers per second. That mechanism was only identified in 1951 by a German astrophysicist named Ludwig Biermann, who noticed that ion tails responded far too quickly and far too violently to changes in solar activity for light pressure to be the cause. Something with far more momentum per unit of energy had to be doing it. The solar wind was inferred from the behavior of comet tails before any spacecraft ever flew through it. The broader, paler tail is the dust tail, and that one is the one Kepler was right about. It is made of solid grains, most of them a few micrometers across, released from the comet's surface as its ices sublimate. Those grains are pushed outward by sunlight, not by particles, not by a wind, not by anything you could call a substance in the ordinary sense, by light. The dust tail curves gently, because each grain, once it is released, is following its own orbit around the sun, while being pushed outward at the same time, and the curve you see is the accumulated record of grains, released at different times, taking slightly different paths. So Kepler was right about the phenomenon, and half right about the cause, which is roughly the best anyone could have managed in 1619. And that half is the half this entire video is built on. Here is why it matters, and here is where the trouble starts. If sunlight is pushing those dust grains outward, then sunlight is transferring momentum to them. That is what pushing means. You cannot change something's motion without giving it momentum. The two statements are the same statement. And if light can transfer momentum, then light must have momentum to transfer, because momentum is a conserved quantity. It does not appear from nowhere. If the dust grain gains some, something else lost some, and the only candidate in the vicinity is the light itself. But light has no mass. That is not a controversial claim or an exotic one. It is in every textbook, on every chart of fundamental particles, in every introductory course. The photon is massless. It is one of the very few particles in the entire catalogue of physics that is listed with a mass of exactly 0. And the formula everybody learns in the first weeks of the first physics class they ever take is that momentum equals mass times velocity. 0 times anything is 0. Light travels at the fastest speed anything can travel, and its mass is 0, and 0 times 300 million meters per second is still 0. By the only rule most people have ever been given for what momentum is, light cannot have any. Not a small amount. None. And yet the tail points away from the sun. I want to sit with that for a moment, because it is easy to skate past it as a curiosity, and it is actually one of the strangest situations in all of physics. We have a quantity, momentum, that is among the most rigorously conserved things in the universe, conserved so exactly that when it appeared to go missing in a particular kind of radioactive decay, in the 1920s, physicists eventually invented an entirely new particle, rather than accept that momentum had simply vanished. We have a formula for that quantity that every educated person knows. And we have an object, light, which flatly refuses to obey the formula while obeying the conservation law perfectly. Something is wrong, and the thing that is wrong is not the comet, and it is not the conservation law. Over the next 2 hours, we are going to take this apart very slowly. We are going to look at how the push was predicted from pure theory decades before anyone could detect it, and at the 27-year gap between the prediction and the first honest measurement, and at the famous little toy that appeared to prove the whole thing and was actually doing something else entirely. We are going to find out what part of a light wave is physically responsible for the push, which is a question with a specific and rather beautiful answer that almost nobody is ever told. We are going to derive the momentum of light from scratch, using nothing more advanced than the electromagnetism you would meet in a decent secondary school, and we are going to do it slowly enough that it makes sense rather than merely being true. And then, near the end, we are going to find the place where all of this stops working, because there is a question about the momentum of light that physics has been arguing about since 1909, that has excellent experiments supporting both of the incompatible answers, and that is not settled tonight. It is not a gap in the popular explanation, it is a gap in the theory. But first, before any of that, we have to go back and look at the formula itself. Because the reason light seems impossible is not that light is impossible, it is that the rule you were handed was never the rule at all. Momentum equals mass times velocity. You learned that early. It is one of the first equations anyone meets in physics, usually somewhere around the age of 13 or 14, and it is taught with a confidence that makes it feel less like a formula and more like a definition. Momentum is mass times velocity. That is what momentum is. It has the reassuring quality of a dictionary entry. And it is correct. That is the part that makes this difficult. Nobody lied to you. If you take a bowling ball of 7 kilograms rolling at 5 meters per second, its momentum is 35 meters per second, and if it hits something, that is exactly how much push it delivers. The formula works. It has worked for every object anybody has ever measured under ordinary conditions. It built bridges and aimed cannons and put people on the moon. But there is a difference between a formula that works and a formula that defines, and the entire strangeness of tonight's subject lives in that gap. Let me try an analogy, and I want to be careful with it, because analogies in physics are usually where the trouble starts. But this one is honest. Imagine you grew up on an island. It is a reasonably large island, with a reasonably large population, and it has dogs. Hundreds of them, all over the place, in every household. And every single one of them is brown. Not roughly brown, brown. Every dog you have ever seen, every dog your parents ever saw, every dog in every story anyone on the island tells, is brown. And so at some point, quite naturally, and without anybody ever deciding it, brownness becomes part of what a dog is. Not a fact about the dogs you happen to have met, a property of dogs. If someone described an animal to you and it was white, you would not think, "Phew, that is an unusual dog." You would think, "That is not a dog." Now somebody rows in from somewhere else with a white dog in the boat. There are two things you can conclude. One is that this creature, whatever it is not a dog, because dogs are brown. The other is that you have been generalizing from a sample, and the sample was never representative, and you had no way of knowing that, because the sample was everything you had. That is what happened with momentum equals mass times velocity, and the island is bigger than you think. The island is every object that has ever been thrown, dropped, rolled, fired, or collided with in the entire history of human experience, up until roughly the year 1900. Every one of those objects had mass. Every one of them moved at a speed that was, compared to the speed of light, essentially zero. Not slow, zero. A rifle bullet travels at about 1/1,000,000th of the speed of light. A spacecraft on its way to Jupiter travels at about 1/10,000th. On the scale that matters here, everything humans have ever handled is standing perfectly still. So of course momentum looked like mass times velocity. On that island, it is mass times velocity, to a precision far better than anyone could measure. The formula is not wrong, it is local. And here is the sentence I would like you to carry through the rest of tonight. Momentum equals mass times velocity is not the definition of momentum. It is what momentum evaluates to, for slow objects that have mass. Which raises the obvious question. If that is not the definition, what is? There are two good answers, and I want to give you both, because one of them is the formal one, and the other is the one that actually lets you think. The formal answer comes from the deepest structural result in classical physics, and it says something that has almost nothing to do with mass. Momentum is the quantity that is conserved, because the laws of physics do not care where you are. Run an experiment here, run the identical experiment 3 meters to the left, and you get the identical result. Space does not have special locations. That symmetry, that indifference of physical law to position, is not decorative. It is the reason momentum is conserved at all, and the mathematics that connects the two produces a definition of momentum in which the word mass does not appear anywhere. Mass shows up later when you ask what that conserved quantity happens to equal for a particular kind of object under particular conditions. That is the rigorous answer, and it is worth knowing, because it means the paradox we started with is not a paradox. It is a category error. We took the value of a quantity in one special case and mistook it for the quantity itself. It is worth pausing on how seriously that conservation is taken, because it tells you something about the status of the quantity we are discussing. In the 1920s, physicists studying a particular kind of radioactive decay found that the energy and momentum before the decay did not match the energy and momentum after it. Some of it was simply missing, and the amount that went missing varied from one decay to the next. There were two ways out. One was to accept that conservation is only statistical, that the books balance on average but not in each individual case. The other was to propose that an undetected particle was carrying the missing quantities away. Physics chose the second option. In 1930, Wolfgang Pauli wrote a letter suggesting a particle that had no charge, almost no mass, and interacted so weakly that it would be nearly impossible to detect. He described the proposal as a desperate remedy and apologized for it. He was right, and it took 26 years to confirm. That is how far physicists were willing to go, rather than let momentum go unaccounted for. Inventing an invisible particle was considered less radical than allowing the books not to balance. So when we say that a dust grain's gain in momentum has to come from somewhere, that is not a bookkeeping preference. It is one of the load-bearing walls. But rigorous answers are not always useful answers, so let me give you the other one, and this is the one we are going to build the rest of the night on. Momentum is the capacity to push something and make it move. That is it. If a thing can arrive at another thing and change its motion, it has momentum. A lot of push, a lot of momentum. A little push, a little momentum. No push, none. Notice what that definition does. It says nothing whatsoever about what the pushing thing is made of. It does not require it to be solid, or heavy, or slow, or anything at all. It is a statement about behavior rather than about substance. And behavior is something you can go and check. Because once you define momentum that way, the question stops being philosophical and becomes an experiment. We are no longer asking whether it is conceptually acceptable for something massless to have momentum. We are asking a much simpler and much better question: can light push things? If it can, it has momentum. And the formula was the problem. If it cannot, then the comet tail needs another explanation, and we have a genuinely new mystery. I want to flag something before we go looking for the answer, because it is a small thing that turns out to matter later. Even inside classical physics, on the island, momentum and energy are already tangled together in a way that hints at what is coming. Take momentum equals mass times velocity and square both sides. You get momentum squared equals mass squared times velocity squared. Now divide both sides by the mass. One of the masses on the right cancels, and you are left with momentum squared over mass equals mass times velocity squared. And mass times velocity squared should look familiar because kinetic energy is 1/2 of exactly that. So you can substitute, and what falls out is that kinetic energy equals momentum squared divided by twice the mass. That is a Newtonian result. It was available in the 1600s. And what it says is that energy and momentum are not independent things that happen to both exist. They are two faces of the same physical situation, linked by an equation. Anything with kinetic energy has momentum. Anything with momentum has kinetic energy. Now, that particular version still has a mass in it, sitting in the denominator, which is exactly where you do not want a zero. So it does not solve our problem. I am not offering it as a solution. I am offering it as a warning that the connection between energy and momentum is old, structural, and much tighter than the two separate chapters in a textbook make it look. When we finally get to a version of that relationship that works for massless things, it is not going to be an exotic new law. It is going to be the general form of something that has been sitting there the whole time, wearing a disguise. There is a reason my instinct, and probably yours, is to resist all of this. It is because for ordinary objects, mass really is the thing that gives them their ability to shove. A heavy thing shoves harder. That is not a misconception. That is a correct observation about heavy things. The mistake is a subtler one. It is assuming that because mass is what supplies the push in every case you have examined, mass is what supplies the push in every case there is. So the question we actually need to ask is sharper than the one we started with. It is not, how can light have momentum without mass? It is this. For ordinary objects, mass is what gives them the ability to push. For light, what does? Something must be doing that job. If light can move a dust grain, some specific feature of light is responsible, and that feature has a name and a mechanism, and it is not mass. Finding out what it is took physics a long time. It also required an experiment so delicate that it defeated the best instrument makers in the world for nearly 3 decades. But before anyone could measure it, somebody had to predict it. And the prediction came out of a piece of mathematics that was not about pushing at all. 2 men arrived at the same answer from 2 completely unrelated directions, and neither of them was trying to explain comets. Before either of them, there had been guesses. Newton's picture of light as a stream of tiny corpuscles made a push seem almost obvious, since a stream of particles hitting a surface is the most ordinary source of pressure there is, and several people said so. In the 1740s, Leonhard Euler, who thought light was a wave rather than a stream, argued that it should still push, and that this was what shaped comet tails. But none of these were predictions in the sense that matters. They were plausible pictures with no numbers attached, and a plausible picture with no number cannot be tested, because it cannot be wrong in any particular way. What changed in the 1870s was that 2 separate lines of argument produced not a picture, but a quantity. The first was an Italian physicist named Adolfo Bartoli, and his argument, published in 1876, is one of the most elegant pieces of reasoning in 19th century physics, precisely because it uses almost nothing. Bartoli did not need to know what light was. He did not need Maxwell's equations, or a wave theory, or a particle theory. He needed only the second law of thermodynamics, which says that heat does not spontaneously flow from a cold body to a hot one. His argument goes roughly like this. Imagine two bodies at different temperatures, both radiating, and imagine a movable mirror between them. If radiation exerted no pressure, you could move that mirror around freely, at no energy cost, and by moving it in the right pattern, you could funnel radiation from the cold body to the hot one, making the hot one hotter and the cold one colder, without doing any work at all. That is exactly the thing the second law forbids. It is a perpetual motion machine of the second kind. The only way to close the loophole is for radiation to push on the mirror. If it pushes, then moving the mirror against the radiation costs work, and the books balance, and the second law survives. So radiation pressure had to exist, not because anyone had seen it, but because thermodynamics collapses without it. That result was so structurally important that when Ludwig Boltzmann derived the law relating a hot body's temperature to how much it radiates, the relationship that now carries his name alongside Stefan's, published in 1884, he built the derivation on Bartoli's radiation pressure and said so explicitly. The pressure of light was load-bearing in the foundations of thermodynamics for years before anybody detected it. The second route to the same conclusion came from James Clerk Maxwell, and it came out of a set of equations that had been written down to describe something else entirely. Maxwell had spent the 1860s assembling the mathematics of electricity and magnetism into a single unified structure. What he found, buried in that structure, was that a disturbance in an electric field creates a magnetic field, and a disturbance in a magnetic field creates an electric field, and the two together can sustain each other and travel. When he calculated how fast such a self-sustaining disturbance would move, using numbers measured in laboratories by people doing experiments with wires and magnets, he got a speed that matched the measured speed of light to within the precision of the day. Light was an electromagnetic wave. Nobody had suspected it. That is the famous part. The part that concerns us is less famous and comes later, in his great 2-volume treatise of 1873, in a section on the mechanical action of light. Maxwell worked out what happens when one of these waves meets a surface and is absorbed, and found that the wave delivers not only energy but a force. The pressure on a perfectly absorbing surface, he showed, is equal to the intensity of the light divided by the speed of light. Divided by the speed of light. Hold on to that, because that division is going to come back at the very center of tonight. Now let us put a number on it, because the number is the whole reason the next chapter of this story took as long as it did. Sunlight arriving above the Earth's atmosphere carries about 1,361 watts per square meter. Divide that by 300 million meters per second, and you get a pressure of about 4.5 micropascals. If the surface is a perfect mirror rather than a perfect absorber, the light comes back out again, which means twice the momentum change, so about 9 micropascals. A micropascal is a millionth of a pascal. To give that some footing, the atmospheric pressure you are sitting in right now, the ordinary weight of air, is about 101,000 pascals. Sunlight pressure is roughly 22 billion times smaller. Let me put it on your body instead. Lie down outside on a clear day. Sunlight at ground level, after the atmosphere has taken its share, delivers around 1,000 watts per square meter. You are presenting maybe 7/10 of a square meter to the sky. The total force of sunlight pushing you down into the grass is about 2/millionths of a newton, which is the weight of about 1/4 of a milligram, something like 1/100th of a single grain of rice. That is the push. That is the entire effect. Everything in this video, every star held up by it, every asteroid steered by it, every atom cooled by it, is that. And here is the number I find most useful for calibrating how weak this is. Suppose you wanted to hold up a paperclip, 1 gram, sitting on your desk. You want to levitate it using nothing but a beam of light shining upward from underneath, absorbed by the metal. The relationship is simple. The force you get is the power of the beam divided by the speed of light. Turn it around. To produce a given force, you need that force multiplied by the speed of light in watts. A paperclip weighs about 1/100th of a newton. Multiply by 300 million, 3 megawatts. To hold up a single paperclip, you need a light source producing about 3 million watts, comparable to a small power station, focused on one paperclip. Every newton of thrust you want from pure light costs 300 megawatts. A household light bulb, radiating in all directions, produces a total thrust of about 30 nanonewtons, which is roughly the weight of a bacterium. It is worth doing the same calculation for the whole planet, because the result is a useful anchor for later. The Earth presents a disk to the Sun, about 12,700 kilometers across, which works out to a cross-sectional area of roughly 127 trillion square meters. Multiply by 4.5 micropascals, and you get a total force of about 580 million newtons of sunlight pressing on the Earth, continuously and always directly away from the Sun. That sounds enormous. Compare it to the Sun's gravitational grip on the Earth, which is about 35,000 billion newtons, and it stops sounding enormous. Radiation pressure is smaller than gravity here, by a factor of roughly 60 trillion. It is a real force. It is included in high-precision solar system models, and it is utterly irrelevant to whether the Earth stays in orbit. Keep that ratio in mind, 60 trillion to 1. It is not a constant of nature, and later tonight we are going to watch it change until light wins. This is why nobody had ever noticed. It is not that the effect is subtle in the way that a faint color is subtle. It is that in every ordinary situation, the push from light is smaller than the vibration from someone walking past in the next room, smaller than the pressure of the air, smaller than the convection currents rising off a warm surface, smaller than essentially everything else happening in the vicinity by an enormous margin. Maxwell had predicted a force. He had also, without meaning to, predicted an experimental nightmare. There is one more piece of theoretical machinery worth mentioning before we go into the laboratory, because it makes the whole picture cleaner, and it comes from a student of Maxwell's approach. In 1884, John Henry Poynting worked out how energy flows in an electromagnetic field and produced a quantity that points in the direction of energy flow and whose size tells you the rate. That quantity is now called the Poynting vector, and it does something rather beautiful. Divide it by the speed of light squared, and you get the density of momentum stored in the field, which means the momentum is not something the light acquires when it hits matter. The momentum is in the field, traveling with it, at every point along its path, whether or not there is anything there to push. Right now, in the air of the room you are in the space between you and the nearest lamp, there is momentum. It is stored in the electromagnetic field, moving at the speed of light, and it is passing through you continuously. Nobody had ever measured any of it. And measuring it was about to take 27 years, defeat a series of very good experimentalists, and produce one of the most famous scientific instruments ever built. An instrument that appeared to prove the whole thing, and was, in fact, proving nothing of the kind. There is a small glass bulb that has been sold in museum shops and science catalogues for 150 years. Inside it, on a needle point, sits a set of 4 little vanes, arranged like a weather vane, each one black on one face and shiny silver on the other. Put it on a windowsill in sunlight, and the vanes spin, sometimes quite fast. Put it in shadow, and they stop. William Crookes built the first of these in the early 1870s. He was not trying to demonstrate radiation pressure. He was trying to weigh things very precisely, and kept finding that his samples appeared to change weight when they were warm, which led him into a study of what happens in near vacuums. The device became famous almost immediately, and it acquired a reputation it did not earn. For years it was presented, in lectures and in books, as the visible proof that light pushes. It is not. And the reason it is not is one of the most useful lessons in the history of experimental physics, because it turns on a detail anyone can check. Think about which way the vanes ought to turn if radiation pressure were driving them. The silvered face reflects light. Reflection means the light arrives, stops, and leaves again in the opposite direction, so the change in the light's momentum is twice what it would be if the light were simply absorbed. Double the momentum change means double the force. So radiation pressure pushes hardest on the shiny side, and the shiny faces should retreat, meaning the vanes should turn with the black faces leading. Every real Crookes radiometer turns the other way. The black faces retreat, the shiny faces lead. The device is not measuring light pressure, it is measuring something bigger that happens to be sitting in the same bulb. The black faces absorb more light and run warmer. Inside the bulb, there is not a true vacuum, but a thin residue of gas, and gas molecules that strike a warm surface rebound with more energy than they arrived with. At the particular density Crookes happened to leave in his bulbs, this thermal effect produces a force on the vanes hundreds or thousands of times larger than the radiation pressure, and in the opposite direction. Osborne Reynolds worked out the mechanism and submitted a paper on it to the Royal Society in 1879, describing what he called thermal transpiration, the tendency of a rarefied gas to creep along a surface from the cold end toward the hot end. The referee assigned to that paper was Maxwell. Consider his position for a moment. Maxwell had predicted radiation pressure 6 years earlier from his own equations. Here was a famous, popular, widely cited instrument that appeared to confirm him, sitting in lecture halls all over Europe. And here was a paper explaining that the instrument was doing something else. He accepted it. More than accepted it, he engaged with the physics so thoroughly that he wrote his own analysis of stresses in rarefied gases arising from differences in temperature, going further than Reynolds had, and submitted it himself. That paper turned out to be the last scientific work he ever published. He died in November of 1879, aged 48. I want to sit on that for a moment, because it is not a small thing. The man who predicted that light pushes spent some of the final months of his life carefully explaining why the object that appeared to prove it was actually measuring warm gas. He had every professional reason to let it stand. Nobody would have accused him of anything. He simply did not want a confirmation he had not earned. That instinct, the refusal of a convenient result, is the thing that separates the physics in this video from the many confident-sounding explanations that have circulated alongside it, and it left the actual measurement still undone. It took another 20 years. Picture the room where it finally happened. You are in a laboratory in Moscow in the last months of 1899. It is not a large room. There is a vacuum pump running, and it has been running for a long time, because getting to the pressure this experiment needs takes hours, and the pressure has to be exactly right. Too much gas, and the effect that ruined the radiometer swamps everything. Too little, and the vanes take so long to shed heat that they drift. On the bench sits a sealed glass vessel. Inside it, hanging from a fibre so thin it is barely visible, is a small horizontal arm with 2 tiny discs of metal at its ends, each a few millimeters across. Attached to the arm is a mirror the size of a fingernail. A lamp throws a narrow beam onto that mirror, and the reflected spot lands on a scale several meters away across the room, where a tiny rotation of the fibre becomes a visible movement of light. Pyotr Lebedev is waiting. He is waiting for the building to be still. Footsteps in the corridor register on the scale. A door closing registers. The temperature of the room drifting by a fraction of a degree registers. He is trying to detect a force of a few billionths of a Newton, and everything in the world is louder than that. Then the beam is admitted, and it strikes one of the discs, and out across the room the spot of light slides a small distance along the scale and settles. That is the moment. That is a physical push, delivered by light, being seen for the first time by a human being. It looks like nothing. It looks like a smudge of lamplight moving a few millimeters on a piece of paper, and the number it produced agreed with Maxwell's prediction to within about 20%. Lebedev published the full account in Annalen der Physik in 1901. What made his work credible was not the deflection itself, which others had seen and mistrusted, but the enormous care he took to prove that the deflection was not the radiometer effect in disguise. He used vanes of different thicknesses on the reasoning that the light pressure should not care about thickness, but the thermal effect should. He reversed the direction of illumination. He varied the residual gas pressure systematically and showed how the two effects behaved differently as he did. Almost simultaneously and entirely independently, Ernest Fox Nichols and Gordon Ferry Hull at Dartmouth College in New Hampshire were doing the same thing with a somewhat more refined apparatus. They announced results in 1901 and published detailed papers in 1901 and 1903. Their treatment of the residual gas problem was more systematic still, and their numbers were tighter. 2 groups, 2 continents, no communication, same answer. The instrument they both used deserves a mention of its own, because it keeps appearing at exactly these moments. A torsion balance is nothing more than a weight hanging from a thin fiber, arranged so that a horizontal force twists the fiber, and the twist can be read off. Coulomb used one in the 1780s to establish the inverse square law of electric force. Cavendish used one in 1798 to measure the gravitational attraction between 2 lead spheres, and through that, the density of the Earth. Eötvös used one at the end of the 19th century to show that gravitational and inertial mass are the same to extraordinary precision. And Lebedev, Nichols and Hull used one to catch light in the act of pushing. 4 of the most delicate measurements in the history of physics, each one made with a weight on a string. There is something almost stubborn about it. Lebedev did not stop there. Measuring radiation pressure on a solid vane is difficult. Measuring it on a gas, where there is no surface to push and the effect has to be inferred from the behavior of the gas itself, is considerably harder. He did it anyway, publishing in 1910. 2 years later, he was dead, at 46. He had resigned his position at Moscow University in 1911, along with a large group of colleagues, in protest at government interference in the institution, and had been working in improvised accommodation ever since. The Principal Physics Institute of the Russian Academy of Sciences carries his name. Nichols went on to become president of Dartmouth College, and later of the Massachusetts Institute of Technology, and the sensitive radiometer he designed remained a standard instrument for detecting faint radiation for decades afterward. So Maxwell was right, Bartoli was right, and Kepler had been looking at it since 1619. There is a postscript to this that I find genuinely satisfying. For a century, radiation pressure was the hardest thing in the laboratory to measure, the signal that everything else drowned out. That relationship has now completely inverted. Since the middle of the 2010s, the National Institute of Standards and Technology in the United States has been developing power meters for industrial lasers that work by radiation pressure. You bounce the beam off a mirror, mounted on an extremely precise balance, and you weigh the push. For a laser in the 100 kilowatt class, this is far more practical than the traditional method, which is to point the beam into an absorber and measure how hot it gets, because at those powers, the beam destroys the absorber. The force that defeated the best experimentalists of the 1870s is now a measuring instrument. But notice what none of this has told us. We know light pushes. We have known it with certainty for more than 120 years. We can measure the push to high precision and use it as a standard. We still have not said what, in a beam of light, is doing the pushing? That is a completely different question from whether it happens, and it is the question that almost never gets answered. The usual response is to reach for the algebra, to write down the relativistic energy equation, set the mass to zero, watch two terms cancel, and present the result as though something had been explained. It has not. An equation that produces the right number is not the same as a mechanism, and if you have ever felt vaguely unsatisfied by that derivation, your instinct was correct. So let us go and find the mechanism, and the first thing we have to do is eliminate the obvious suspect. To find out what pushes, we have to look at what a beam of light actually is, and we have to look more carefully than the usual picture allows. You have seen the diagram. It is in every textbook, on every poster, in every animation. There is an arrow running left to right, representing the direction the light is traveling. Wrapped around that arrow are two sine waves, drawn at right angles to each other, one in the vertical plane and one in the horizontal plane. One is labeled E for the electric field, the other is labeled B for the magnetic field. That diagram is correct. It is also, in a specific and consequential way, misleading, not because of what it draws, but because of what happens next. In almost every course, in almost every book, the magnetic field is drawn once, at the start, and then quietly abandoned. Every subsequent calculation is about the electric field. Interference, diffraction, polarization, refraction, absorption, the photoelectric effect, the way antennas work, the way your eye works, all of it is taught in terms of the electric field, and the magnetic component sits there in the diagram like a decorative feature. There is a reason for that, and it is a good one, which we will get to. But it means that the magnetic field of a light wave is, for most people who have studied physics, the field nobody draws, present in the picture, absent from the thinking. Hold that thought. Now let us ask, what happens when this wave meets matter? Matter, at the level that matters here, is charges. An atom is a small, dense positive nucleus with electrons around it, and the electrons are light, about 2,000 times lighter than even a single proton, and they are the ones on the outside, so they are what the incoming wave meets first and moves most easily. When light strikes a metal foil, or your skin, or a dust grain in a comet's tail, what is physically happening is that an oscillating electromagnetic field is arriving at a population of electrons. The electric field acts first, and it acts in the most straightforward way imaginable. A charge sitting in an electric field feels a force. The force equals the charge multiplied by the field strength. It does not matter whether the charge is moving or stationary. The electric force is there either way. Since the electron carries negative charge, the force on it points opposite to the field direction. But that detail will not change anything important. So the electric field of the wave grabs the electron and pushes it. In the diagram we have been describing, the electric field is oscillating vertically, so the electron gets pushed up. And at this point, the obvious conclusion presents itself, and I want to walk into it deliberately, because it is exactly where most people's intuition goes, and it is exactly wrong. The obvious conclusion is, there it is. The electric field is pushing the electron, therefore the light is transferring momentum to the electron, therefore that is where the momentum of light comes from. Question answered, and we can all go to sleep. Except it does not work. Watch what happens over a full cycle. The wave is oscillating. That is what makes it a wave. Half a cycle after the electric field pointed up, it points down, which means the electron, which was being pushed upward, is now being pushed downward with exactly the same strength. Half a cycle later it is being pushed up again, and so on, for as long as the light lasts, at a rate of around 500 trillion times a second for visible light. Add all of that up. The upward pushes and the downward pushes are equal in size and opposite in direction, and they alternate. Over any complete cycle, they sum to precisely zero. The electron ends up exactly where it started, moving exactly as it was. The electric field is not delivering any net momentum. It cannot. It is oscillating, and an oscillating force delivers a net momentum of zero by construction, no matter how strong it is. And notice that this is not a technicality about our particular diagram. Turn the polarization, rotate the wave, tilt the geometry, and the same argument survives, because the electric field of a light wave always points across the direction of travel, never along it. Even if it did not average out, it would be shaking the electron sideways relative to the beam. It could never push the electron along the beam, which is the direction the comet's dust actually goes. So the electric field is eliminated, twice over, which leaves us in an uncomfortable position, because the electric field is the part of light that does almost everything else. I want to be careful here, because eliminated does not mean irrelevant. The electric field is doing something enormously important in this interaction, and if we lose track of it, we will not be able to finish the derivation later. What the electric field is doing is delivering energy. Think about what it means to grab an electron and shake it. Before the light arrived, the electron was sitting more or less still. Now it is oscillating. Oscillating means moving, and moving means kinetic energy, and that energy came from somewhere. It came from the wave. The electric field is doing work on the electron, pushing it while it moves, and work is energy transfer. This is not an abstraction. This is why sunlight is warm. When light falls on your skin, the electric field of the wave sets the charges in your skin oscillating. Those oscillations get randomized by collisions with everything around them. Randomized molecular motion is what temperature is, and you feel heat. The entire experience of standing in the sun and feeling warmth is the electric field of light doing work on the electrons in you. So we have a division emerging, and it is worth stating plainly before we go further, because it is the shape of the answer. The electric field delivers energy. It does not deliver momentum, which means something else has to deliver the momentum. And there is only one other component in the wave. It is worth knowing how big these fields actually are, because the numbers make the neglect of the magnetic component look reasonable, rather than careless. In full sunlight, the peak electric field of the light wave is around 1,000 volts per meter. That is not a small field. It is comparable to the field under a thunderstorm cloud, and it is arriving at every square centimeter of you, oscillating hundreds of trillions of times a second. The magnetic field of that same wave has a peak strength of about 3.5 microsesla. The Earth's own magnetic field, the one that moves a compass needle, is around 50 microsesla. So the magnetic component of full sunlight is roughly 15 times weaker than the ordinary background magnetic field of the planet you are standing on, and it is reversing direction so rapidly that no compass could ever respond to it. That is the field we are about to make responsible for one of the most consequential effects in physics. It is 15 times weaker than the field that has been pointing north your whole life, and it is the reason stars do not collapse, asteroids drift off course, and atoms can be brought to a standstill in a laboratory. Now, before I turn to it, I want to name the objection, because if you have any physics background, you are probably already making it. The objection is, the magnetic field oscillates too. It is the other sine wave in the same picture, going through its own cycle at the same frequency, flipping direction just as often. If an oscillating electric force averages to zero, why on earth would an oscillating magnetic force behave any differently? That is a completely fair objection, and it is the reason this mechanism is not obvious, and it is the reason the answer is genuinely surprising rather than merely technical. The resolution is that the magnetic force is not like the electric force. It is a different kind of force, with a different rule, and the difference is exactly the thing that saves us. An electric field pushes a charge along the field direction, always, whether the charge is moving or not. A magnetic field does neither of those things. A magnetic field exerts no force at all on a stationary charge. It only acts on charges that are already moving. And when it does act, the force it produces is not along the field and not along the motion. It is perpendicular to both. Read that again, because it contains everything. The magnetic force depends on the velocity of the charge. And what has the electric field just been doing? Giving the electron a velocity. So the two components of the wave are not two independent forces acting side by side. They are working in sequence. The electric field sets the electron moving, and the magnetic field acts on the motion that the electric field just created. The second force cannot exist without the first. That coupling is what breaks the symmetry, and it is why the magnetic force does not average away. But seeing exactly how it does not average away requires us to be very careful about directions, and directions in magnetism are notoriously the place where people's confidence outruns their accuracy. So we are going to do it slowly. We are going to take one electron, put it in a light wave, and follow it through both halves of a single oscillation, working out the direction of the magnetic force at each stage. It is the most important 60 seconds of physics in this entire video, and when it lands, you will never look at that textbook diagram the same way again. The rule we need is called the Lorentz force law, and despite the imposing name, it is something you would meet in a good secondary school physics course. It says that the force a magnetic field exerts on a charge is equal to the charge multiplied by the speed of the charge multiplied by the strength of the magnetic field and directed perpendicular to both the velocity and the field. That perpendicularity is the whole character of magnetism. An electric force pushes you along the field. A magnetic force pushes you sideways to everything. The direction is found with a rule involving your right hand, and I am going to describe it carefully because we are about to use it twice, and the second time is where the surprise lives. Hold your right hand flat, fingers together, thumb sticking out to the side. Point your fingers along the direction the charge is moving. Now curl your fingers toward the direction the magnetic field points. Your thumb now points along the direction of the force, for a positive charge. For a negative charge, an electron, the force is in exactly the opposite direction to your thumb. That is all of it. Fingers along the velocity, curl toward the field, thumb gives the force, reverse for an electron. Now let us take our light wave and one electron and go through a cycle. The wave is traveling to the right. Let the electric field oscillate vertically, up and down, and therefore the magnetic field oscillates horizontally, into the page and out of the page. These are locked together. They rise and fall in step, and they reverse together. First half cycle. The electric field points downward. Our electron is negative, so the electric force on it points upward, and the electron starts moving upward. At this same instant, the magnetic field points into the page. Apply the rule. Fingers up, along the electron's velocity. Curl them into the page, toward the magnetic field. Your thumb points to the left, but this is an electron, so reverse it. The force is to the right. To the right is the direction the wave is traveling. The electron is being pushed forward, along the beam, in the direction the light is going. Now the second half cycle, which is the moment of truth. The wave has moved on half a wavelength. The electric field has reversed, and now points upward, so the force on our negative electron points downward, and the electron is now moving down. But the magnetic field has reversed too. It has swung around to point out of the page. Apply the rule again. Fingers down, along the velocity. Curl them out of the page, toward the field. Your thumb points to the right. Reverse it, because electron. The force is to the left. No. Let me do that again properly. Because this is precisely where people go wrong, and I would rather be slow than slick. Fingers pointing down, curling toward a field that comes out of the page, means rotating your hand so the fingers sweep outward toward you. Do it, and your thumb points left. Reverse for the negative charge, and the force is to the right. To the right. Again. Both halves of the cycle push the electron the same way, forward, along the direction the light is traveling. And that is the answer. That is the whole mechanism. Look at why it happens, because the reason is almost embarrassingly simple once you see it. The magnetic force depends on two things that both reverse. The electron's velocity flips, and the magnetic field flips. In the cross product that determines the direction, two sign changes cancel each other exactly. The force comes out the same. The magnetic force does not oscillate. It rectifies. That word is worth keeping. In electronics, a rectifier is a device that takes an alternating current, which goes back and forth and averages to nothing, and turns it into a current that flows one way. That is precisely what the magnetic component of a light wave does to the motion the electric component creates. The electric field supplies a back and forth. The magnetic field converts it into a steady, one-directional shove. Now let us stop being abstract about it. Close your eyes for a moment, if they are not closed already, and become the electron. You are sitting in a metal foil, one of an unimaginable number of others like you, essentially still. Then the light arrives. It does not arrive as a beam or a glow. From where you are, it arrives as a field, filling the space you occupy, and the first thing you feel is a lift. The electric field takes hold of you and carries you upward, and as you rise, something else happens that has nothing to do with rising. The moment you have any upward speed at all, the magnetic field takes that speed and turns it. You feel a second push, at right angles to the first, forward, along the direction the light came from. You reach the top of your rise. The electric field lets go, reverses, and pulls you back down. Now you are falling. And here is the strange part. You would expect the sideways push to reverse as well, because everything else has. It does not. As you descend, the magnetic field has also turned over, and the two reversals cancel, and the forward push is exactly where it was. Still forward, still the same direction. Up, forward, down, forward, up, forward, down, forward, 500 trillion times a second. Your vertical motion goes nowhere. You end each cycle exactly where you began, and if that were the only thing happening, the light would leave no trace on you at all. But underneath the oscillation, there is a slow, patient, entirely one-directional drift, so small that in any single cycle it is nothing, and so relentless that it never once cancels. That is what the push feels like from the inside. Not an impact, a rectified shiver. Come back out now, and consider what this means for the foil, rather than for a single electron. Every electron in that material is doing the same thing at the same time. There are on the order of 10 to the 22 of them in a square centimeter of foil, and the wave is not selecting favorites. It is arriving at all of them together, driving all of them together, and rectifying all of them in the same direction. Individually, the force on each one is unimaginably small, but they all point the same way, so they add. And because those electrons are bound into the material, they are not free to simply leave. The force on them becomes a force on the whole foil, transmitted through the electromagnetic bonds that hold the metal together. The foil moves. That is the push Lebedev measured. That is what deflected the spot of light on his scale. That is what strips a comet's dust away and lays it out along a line, pointing away from the sun. There is a refinement here that I want to include rather than smooth over, because it is the sort of detail that makes the picture more trustworthy rather than less. If you set up the problem with a completely free electron in empty space, with nothing to slow it down and nothing to absorb any energy, and you work through the timing carefully, you find that the electron's velocity ends up a quarter of a cycle out of step with the fields driving it. When that happens, the forward force is positive for part of the cycle and negative for the rest, and it averages back to zero after all. That is not a flaw in the argument. It is the argument being exactly right, because a free electron with nothing to damp it does not absorb any net energy from the wave either. It borrows energy and gives it straight back, and the whole result we are building toward says that momentum transfer and energy transfer are two sides of one thing. So if no energy is taken up, no momentum should be delivered. The moment the electron is in real matter, bound to a lattice, colliding with its neighbors, radiating, doing anything at all that takes energy out of the oscillation and puts it somewhere else, its motion acquires a component that is in step with the driving field, and that component is the one the magnetic field rectifies into a lasting push. So the two halves of the story lock together. Where light gives up energy, it gives up momentum. Where it gives up nothing, it pushes nothing. A perfectly transparent sheet of glass, absorbing nothing and reflecting nothing, feels no net force at all. This is not an extra assumption we have to bolt on. It falls out of the same mechanism. I want to say plainly what has happened here, because I think it is genuinely one of the loveliest results in physics, and it is almost never told. Every diagram of light you have ever seen draws two waves. One of them gets all the attention, the electric field, which explains color and polarization and interference and refraction and vision. The other is drawn and then forgotten. And it turns out that the forgotten one, the field nobody draws, in any sense that matters, is the one responsible for the single property of light that looked impossible. There is an honest reason the magnetic field gets ignored, and it is worth stating, because I do not want to leave you thinking that generations of textbook writers were simply careless. The magnetic force in a light wave is smaller than the electric force by a factor of the charge's speed divided by the speed of light. For an electron being wobbled by ordinary sunlight, that ratio is minuscule. The electric effects are overwhelmingly larger, and for any question about how light propagates, or bends, or interferes, or is absorbed, you can ignore the magnetic component entirely and get the right answer to many decimal places. But the electric force averages to zero, and the magnetic force does not. And a tiny quantity that accumulates will always eventually beat an enormous quantity that cancels. Given enough cycles, and there are 500 trillion of them every second, the small, stubborn, one-directional term is the only one left standing. That is a pattern that shows up everywhere in physics once you start looking for it. It is why a coastline can be rearranged by tides that individually do nothing. It is why the tiny asymmetry in the re-radiation of heat from a rotating asteroid, which we will come to later, can move a mountain-sized rock thousands of kilometers out of its orbit. Persistence beats magnitude. So we have a mechanism. The electric field of a light wave delivers energy to a charge and sets it moving. The magnetic field acts on that motion and delivers a steady momentum along the beam. But a mechanism is not yet an equation. We were promised that the momentum of light equals its energy divided by the speed of light. And so far, we have only shown that a push exists and pointed at the component responsible for it. So now, we finish the job. We take what we have just built, put actual quantities on it, and derive the equation from scratch, with no relativity, no quantum mechanics, no appeals to authority, and nothing you would not find in a school textbook. Let us step back for a moment and put the pieces we have on the table together, because we are about to build something out of them, and it helps to see them all at once. We started with a comet whose tail points the wrong way, which told us that something coming from the sun pushes matter. We looked at the formula that made that seem impossible and found that momentum equals mass times velocity is not a definition, but a local habit, true on a small island of slow, heavy things. We replaced it with a working definition. Momentum is the capacity to push. We watched two independent lines of 19th century theory predict a specific, tiny pressure, and watched it take 27 years and a great deal of stubbornness to measure. And then we opened up a light wave and found that its electric field delivers energy, but no net momentum, while its magnetic field, acting on the motion the electric field creates, delivers a steady one-way push. All of that is qualitative. Now we make it exact. We start with the magnetic force, because that is the one doing the work we care about. Its size is the charge, multiplied by the velocity of the charge, multiplied by the magnetic field strength. There is normally a factor involving the angle between the velocity and the field, but in our case, the electron is moving vertically and the magnetic field is horizontal, at 90 degrees to each other. And at 90 degrees, that factor is exactly 1. So the magnetic force is simply charge times velocity times magnetic field. Next, we need to know how strong the magnetic field of a light wave actually is, and this is the second thing we take from school, electromagnetism rather than inventing. In any electromagnetic wave traveling through empty space, the two fields are not independent. Their strengths are locked together by a fixed relationship. The magnetic field equals the electric field divided by the speed of light. This is not an approximation, and it is not a coincidence. It falls directly out of Maxwell's equations when you ask them what a self-sustaining traveling wave has to look like. The two fields are two aspects of one object, and their ratio is fixed by the speed at which that object moves. So substitute. The magnetic force equals the charge times the velocity times the electric field divided by the speed of light. Now rearrange that and group it slightly differently because a familiar quantity is hiding inside it. Charge times electric field is the electric force, the force the electric field is exerting on our electron. So the expression becomes the magnetic force equals the electric force multiplied by the velocity of the electron divided by the speed of light. I want to pause on that line because it is beautiful in its own right, quite apart from where we are going with it. It says that within a light wave, the two forces are not separate phenomena. The magnetic force is the electric force scaled down by the ratio of the charge's speed to the speed of light. Both forces in one relationship, and it tells you immediately why the magnetic component is ignored in nearly every calculation. For anything moving at ordinary speeds, that ratio is a very small number, so the magnetic force is a very small fraction of the electric one. It is not important because it is large. It is important because it is the one that does not cancel. Now look at the top of that expression. The electric force multiplied by the velocity of the electron. Force multiplied by distance is work. It is the standard measure of how much energy you transfer when you push something through a distance. Force multiplied by velocity is the same quantity per unit time, which is to say power, the rate at which energy is being delivered. And what is being delivered energy here? The electron. By what? By the electric field of the wave. So the top of our expression is precisely the rate at which the light is pouring energy into the electron, in joules per second. Now look at the left-hand side, the magnetic force. Force, in its original and most general definition, is the rate of change of momentum. Newton did not write his second law as mass times acceleration. He wrote it in terms of the change in the quantity of motion. Force is how fast momentum is being handed over. So read the whole equation again with those two translations in place. On the left, the rate at which momentum is being delivered to the electron. On the right, the rate at which energy is being delivered to the electron, divided by the speed of light. Both sides are per second. Cancel the seconds. The momentum delivered equals the energy delivered, divided by the speed of light. That is the equation. Momentum equals energy over c. We have derived the momentum of light from the Lorentz force law and the field ratio in an electromagnetic wave, and nothing else. No relativity, no quantum mechanics, no four vectors, no invariant intervals, no setting a mass to zero and watching terms disappear. 2 pieces of school physics and a careful look at directions. And unlike the algebraic route, this one tells you what is physically happening at every step. Because now look at what we can say. If you ask which part of the light gave the electron its energy, the answer is the electric field. If you ask which part gave it its momentum, the answer is the magnetic field. 2 components of the same wave, arriving together, inseparable, doing 2 entirely different jobs. That is the sentence I would want somebody to take away from tonight. The warmth you feel standing in sunlight is the electric field of the light doing work on the charges in your skin. The push you do not feel, the 2 millionths of a Newton, the quarter of a milligram, is the magnetic field of that same light, rectifying the motion, the electric field created, and delivering it forward. Every physics education draws both fields on the same diagram and then discusses only one of them for the next several years. The one that gets ignored is the one that answers the question that seemed impossible. You have almost certainly seen that diagram. You almost certainly never once wondered what the other wave was for. Let us also sanity check the result, because a derivation you cannot test on a familiar case is only half convincing. Take a 100-watt light bulb, radiating 100 joules of energy every second. Divide by 300 million, and the bulb is emitting momentum at a rate of about 3/10 of a kilogram meter per second every second. Which is to say, if all the light went one way, the bulb would experience a recoil force of about 1/3 of a micronewton. In reality, a bulb radiates in every direction, so the recoils cancel and it sits still. But shine the same power in one direction, and that is your thrust. Now check the other end of the scale. A single photon of green light, at a wavelength of 500 nanometers, carries about 410 billion billionths of a joule of energy. Divide by the speed of light, and its momentum comes out to roughly 1.3 times 10 to the minus 27 kilogram meters per second. That is a number with no useful comparison in ordinary life. A single grain of sand creeping across a table at a centimeter a second has something like 10,000 billion times more momentum than that photon. And you can get to the same number by a completely different route. Divide Planck's constant by the wavelength, and you get exactly the same answer, because the energy of a photon is Planck's constant times the frequency, and frequency times wavelength is the speed of light. The quantum relation and the classical relation are the same relation, wearing different clothes. That quantum version has a direct experimental check, and it is probably the cleanest single piece of evidence that light carries momentum in individual packets. In 1923, Arthur Compton fired X-rays at a block of graphite and measured the radiation that came back out at various angles. What he found was that the scattered X-rays had a longer wavelength than the ones that went in, and that the amount of stretching depended on the angle in a very specific way. Longer wavelength means lower energy. The X-rays were losing energy in the encounter. You cannot get that from a wave picture. A wave should scatter off a target at the same frequency it arrived with. But you can get it, exactly, if you treat the X-ray as a particle with a momentum of Planck's constant over its wavelength, and treat the encounter as an ordinary elastic collision between 2 billiard balls, one of them a photon, the other a loosely bound electron. Work out the collision with conservation of energy and conservation of momentum, and the predicted wavelength shift matches the measurement at every angle. The characteristic scale that comes out of that calculation, about 2.5 trillionths of a meter, is now called the Compton wavelength of the electron, and it appears throughout modern physics. Compton received the Nobel Prize in 1927. His result was resisted for several years, and one of the most determined attempts to disprove it, by William Duane at Harvard, ended when Duane found the error in his own apparatus and publicly conceded. There is one more thing to notice about the equation itself, and it is the part that quietly explains the whole history we have just been through. The division by the speed of light is not decoration. It is the reason none of this was obvious for 400 years. The speed of light is an enormous number in the units human beings use, because human beings evolved at walking pace. When you divide any ordinary amount of energy by 300 million, you get an amount of momentum that is, by everyday standards, nothing at all. Light carries plenty of energy, enough to warm you, to burn you, to run the entire biosphere. It just carries that energy in the form that has the worst possible exchange rate into push. So the answer to the question we started with is not that light is strange. Light is behaving exactly as a field carrying energy should behave. The answer is that we live inside a very particular corner of the universe, where things are slow and heavy, and light is unimaginably fast, and in that corner, one term is huge and the other is invisible. Which raises the question of what the general rule actually looks like, the one that covers both the bowling ball and the photon without special cases. That rule exists. It has existed since 1905, and it retires mass times velocity in a way that is more thorough than most people realize. There is a single equation that covers every case, the bowling ball, the photon, the proton, in a particle accelerator moving at 99.99% of the speed of light, and a stone sitting perfectly still on a table. It is not famous, which is a small tragedy, because the equation that is famous is one of its special cases. It says that energy squared equals momentum times the speed of light squared plus mass times the speed of light squared. Two terms, one built out of momentum, one built out of mass. Add them in quadrature and you get the square of the total energy. Now watch what happens when you put things into it. Take an object that is not moving. Its momentum is 0, so the first term vanishes, and you are left with energy squared equals mass times the speed of light squared, all squared. Take the square root, and you have energy equals mass times the speed of light squared. That is the famous equation. That is not the general law. It is the general law with the momentum switched off, which is to say, it applies to things that are standing still. Now take a photon. Its mass is 0, so the second term vanishes, and you are left with energy squared equals momentum times the speed of light, squared. Take the square root. Energy equals momentum times the speed of light. Rearrange. Momentum equals energy divided by the speed of light. There it is again. The same result we derived the hard way, out of the magnetic force and the right-hand rule, falls out of this equation in one line. And this is exactly the derivation I would warn you about if you had come across it on your own, because it is the one that leaves you feeling cheated. It is correct, it is fast, and it explains nothing whatsoever. It tells you that if you set a symbol to 0, two terms cancel, and a particular expression remains. It does not tell you what is pushing. That is the difference between a derivation and an understanding, and I think it is worth naming clearly, because it is the reason this video exists. Physics is full of results that can be obtained in one line from the right starting point, where the one line teaches you nothing at all. The starting point contains the answer already. If you want to know why the world is like that, you have to go around the long way, and the long way is what we did in the last 2 chapters. But the general equation does do one thing beautifully, and that is to show you exactly where mass times velocity comes from, and exactly how far it can be trusted. Take an ordinary object with mass, moving slowly. Its energy is dominated by the mass term, overwhelmingly so, because the speed of light squared is such an enormous multiplier. The momentum term is a tiny correction sitting on top. If you expand the equation for that case, keeping only the leading corrections, you get something with a familiar shape. The total energy comes out as the mass term, plus 1/2 of mass times velocity squared, plus progressively smaller terms that nobody ever mentions. 1/2 of mass times velocity squared. Kinetic energy. The formula from school falls out as the first correction term in an expansion, and the same expansion produces momentum equals mass times velocity as the leading approximation, with corrections that grow as the speed rises and become enormous as you approach the speed of light. So the formula you learned is not merely a special case in some vague philosophical sense. It is literally the first term of a series. There are more terms. You were never shown them, because for anything you will ever throw, they are smaller than the width of the chalk line. I said earlier that momentum equals mass times velocity is a rule from an island where every dog is brown. Now we can be precise about where the island ends. The correction to that formula is a factor that depends on how fast you are going compared to the speed of light. At walking pace, that correction differs from 1 by about 1 part in 100,000 billion billion. At the speed of a fired bullet, about 1 part in 1,000,000 million. At the speed of a spacecraft leaving Earth, about 1 part in 1,000,000,000. It is not until you reach a substantial fraction of the speed of light that the correction becomes something you could notice, and by then it is not a correction anymore. It is the whole story. Everything humans handled for the first 200,000 years of our existence lived on the flat part of that curve. Of course we thought it was a law. Now I want to go one level deeper than the equation, because there is a still more general answer to the question of what momentum is, and it does not involve mass, velocity, energy, or the speed of light. In 1918, Emmy Noether proved a result that reorganized the foundations of physics. What she showed is that every continuous symmetry of a physical system corresponds to a conserved quantity, and the correspondence is exact and constructive. Give her a symmetry, and she will hand you back the thing that is conserved because of it. The relevant symmetry here is the simplest one imaginable. The laws of physics do not depend on where you are. An experiment run in this room and the identical experiment run 3 meters to the left give identical results. Space has no preferred addresses. The conserved quantity that follows from that symmetry is momentum. That is the definition. Momentum is the thing that is conserved because space does not care where you are. Nothing in that sentence mentions mass, and nothing in the mathematics behind it does either. Mass appears only when you take that general conserved quantity and ask what value it takes for a slow lump of matter. Which means the question we started with tonight, how can something with no mass have momentum, was never a question about light. It was a question about a definition we had accepted without reading the small print. Light has momentum because space is uniform, and light carries energy through it. The absence of mass is not an obstacle. It was never in the job description. I find that reframing does something odd and rather uncomfortable, and I want to sit with the discomfort rather than move past it, because it is the real subject of tonight. Consider how confidently you would have said, before this video, that momentum is mass times velocity. Not as a guess, as a fact. It was taught to you as a fact, it worked every time you used it, and nothing in your experience ever contradicted it. And it is a special case that fails badly the moment you leave the small region of the universe where humans happen to live. Now ask how many other things you believe are in that category. That is not a rhetorical flourish. Physics has done this repeatedly. Kinetic energy equals half mass times velocity squared, an approximation, valid at low speed. Time intervals are the same for everybody. An approximation, valid at low speed. Mass is conserved in chemical reactions, an approximation, accurate to about 1 part in 1,000,000,000 and no further. Velocities add by simple addition, an approximation. Every one of these was taught, for a period, as a law. Every one of them turned out to be the flat part of a curve. There is a pattern in how they fail, too, and it is consistent. They do not fail by being slightly off. They fail by being exactly right in one domain and completely inapplicable outside it. And the boundary is invisible from inside, because inside the domain there is nothing to compare against. That is what the brown dogs were about. Not that the islanders were foolish. They had no white dogs. There was nothing available to them that could have revealed the assumption they were making, because the assumption was not visible as an assumption. It looked like a description. Before we leave the general picture, there is one more thing light carries that almost nobody hears about, and it makes the point that linear momentum is not a special exception, but one instance of something broader. Light also carries angular momentum. It can make things spin. Richard Beth demonstrated this at Princeton in 1936 in an experiment of remarkable delicacy. He suspended a thin plate of birefringent material from a quartz fiber and shone circularly polarized light through it. Circularly polarized light has an electric field that does not oscillate back and forth along a line but rotates, corkscrewing as it travels. Passing it through the plate changed the handedness of that rotation, which meant angular momentum had to be transferred to the plate. Beth measured the resulting twist. The torque was on the order of a 10,000 billionth of a Newton meter, a number so small that he had to drive the system at its resonant frequency and let the effect accumulate over many cycles to see it at all. Per photon, the amount is a fixed quantum, Planck's constant divided by 2 pi. Every photon of circularly polarized light carries exactly that much spin, in one direction or the other, and there is no in-between value. Then in 1992, a group led by Les Allen showed that light can carry a completely separate kind of angular momentum, unrelated to polarization, if the wavefront itself is twisted into a helix like a corkscrew. That variety comes in integer multiples of the same quantum and can be made arbitrarily large. Beams of this kind are now used as optical spanners, rotating trapped microscopic particles on demand, and as a way of packing more information into a single optical fiber. So light pushes and light twists. Neither requires mass. Both are properties of a field carrying energy and structure through space. So here is where we stand. Light has momentum. We know why. Mechanically, the magnetic component of the wave, rectifying the motion the electric component creates. We know the equation, and we have derived it twice, once with physical insight and once with algebra. We know why the effect is so weak that it took 400 years to explain and 27 more to measure. And the natural conclusion is that this is a settled subject, a tidy piece of 19th century physics, confirmed, understood, filed away. It is not, and the rest of tonight is about why. Because before we get to what is unresolved, I want you to see how enormous the settled part is, how this micropascal, this quarter of a milligram, this force too small to feel, turns out to be holding up the largest objects in the universe and rearranging the orbits of mountains. A star is a permanent argument between two things that want opposite outcomes. Gravity is trying to collapse it. Every gram of material in a star is pulling on every other gram, and left alone, that pull would crush the whole object down into something very small and very strange. What stops it is pressure from inside pushing outward, and in a star like the Sun, most of that outward pressure is ordinary gas pressure, hot particles moving fast and colliding. But not all of it. Some of that outward push, in the Sun, is radiation pressure. Photons generated in the core are streaming outward, and on their way they are doing exactly what we spent the last hour describing, encountering charges and pushing them. In the Sun, this contribution is modest, on the order of 1,000th of the pressure at the center. It is a footnote. It stops being a footnote as stars get bigger. The amount of radiation a star produces rises very steeply with its mass, far more steeply than the mass itself. Double a star's mass, and you do not double its output. You increase it by something like a factor of 10. So as you move up the scale of stellar masses, the radiation pressure inside grows much faster than the gravity it is resisting. And somewhere above roughly 20 times the mass of the Sun, radiation pressure stops being a correction and becomes the dominant thing holding the star up. Those stars are unstable. They shed material at enormous rates, they flicker and flare, and they do not last long. There appears to be an upper limit to how massive a star can be, somewhere in the region of a few hundred solar masses, and radiation pressure is a large part of the reason. Build a star bigger than that, and the light it makes tears it apart from the inside. This has a name. It is called the Eddington limit, after Arthur Eddington, who worked it out in the 1920s. The luminosity at which the outward push of radiation exactly cancels the inward pull of gravity. It works out to about 30,000 times the Sun's output for every solar mass of material. Go above it, and the object cannot hold on to its own outer layers. And the Eddington limit does not only apply to stars, it applies to anything that is both massive and bright, which most importantly includes black holes that are actively feeding. Material spiraling into a black hole heats up and radiates ferociously, and that radiation pushes outward on the material still trying to fall in. There is therefore a maximum rate at which a black hole can grow by ordinary accretion. That limit is one of the central problems in modern cosmology, because we observe black holes of 1 billion solar masses existing when the universe was less than 1 billion years old. And if you run the growth calculation with the Eddington limit in place, there is not enough time. Something about our picture is wrong, and the constraint that makes it wrong is the momentum of light. Now let us go the other way, all the way down, because the most interesting thing about radiation pressure is not how big it can get, it is where it wins. I want you to follow a single number as it changes. Start with yourself. You are lying in sunlight, and the light is pushing you with a force equivalent to the weight of about 1/4 milligram. Meanwhile, the Earth is pulling you down with the weight of your whole body. The competition is not close. Gravity wins by a factor of hundreds of millions. Now shrink. Take a pebble. Gravity still wins overwhelmingly, but notice what has happened to the two quantities. The gravitational pull depends on the pebble's mass, and mass depends on volume, which goes as the cube of the size. The radiation push depends on how much area the pebble presents to the light, and area goes as the square of the size. So when you halve the size, gravity drops by a factor of 8, and the light pressure drops only by a factor of 4. Shrink again. A grain of sand. The gap has narrowed. It is still enormous, but it has narrowed. Shrink again. A particle of smoke, invisible individually, a few thousandths of a millimeter across, narrower still. Keep going, down past the resolution of the human eye, down to a particle 100 times smaller than the width of a hair, and somewhere around 1/2 millionth of a meter, 1/2 micrometer, depending on what the grain is made of and how well it reflects. The two lines cross. Below that size, in the solar system, sunlight pushes harder than the sun pulls. Think about what that means. A grain of dust smaller than that threshold, released anywhere in the inner solar system, does not orbit, it is expelled. The sun does not hold it, the sun throws it away. There is a continuous outward flux of these particles, and they have a name, beta meteoroids. They stream outward past the planets and out of the solar system entirely. The same sunlight that cannot move you at all is a wind strong enough to strip matter out of a star system. Nothing about the light changed. The only thing that changed was the size of the thing it was hitting. And the tail points away from the sun. That sentence has been sitting at the start of this video as a mystery. Now it is a receipt. The dust released from a comet is exactly in the size range where light competes seriously with gravity. And what you are looking at when you look at a comet's dust tail is that competition, resolved, written across 100 million kilometers of sky. For the grains slightly too large to be expelled, something subtler happens. They stay in orbit, but they do not stay in the same orbit. A dust grain absorbs sunlight coming radially outward from the sun and re-radiates it in all directions. Because the grain is moving along its orbit, that re-radiation is very slightly asymmetric in the sun's frame, and the asymmetry acts as a drag on the grain's orbital motion. Over tens of thousands to hundreds of thousands of years, the grain spirals inward and is destroyed. This is called Poynting-Robertson drag, and it has a consequence that is easy to overlook. The cloud of fine dust filling the inner solar system, the stuff that produces the faint glow called the zodiacal light, cannot be primordial. It would have drained away long ago. It has to be continuously resupplied by comets and by collisions between asteroids. The dust you see on a very dark night is recent. For objects far too large to be pushed around wholesale, there is a third effect, and it is the one with the most direct consequences for us. A rotating asteroid absorbs sunlight on its day side and radiates the heat away as infrared photons. Those photons carry momentum, so the asteroid recoils. If the emission were perfectly symmetrical, the recoils would cancel, but it is not, because rock takes time to warm up and time to cool down. The hottest part of an asteroid's surface is not the point directly under the sun, it is the part that has been in sunlight for a while, the equivalent of mid-afternoon. So the strongest infrared emission comes off at an angle, and the recoil has a component along the asteroid's orbital motion. The asteroid slowly accelerates or decelerates, depending on which way it spins, and its orbit changes. This is the Yarkovsky effect, named for a Russian civil engineer who described it in a privately circulated pamphlet around 1901, and would have been entirely forgotten if the Estonian astronomer Ernst Opik had not remembered reading it decades later and brought it back into the literature. It has been measured directly. Radar ranging of the asteroid Golevka, reported in 2003, showed that it had drifted about 15 kilometers away from where pure gravity said it should be over 12 years. For the asteroid Bennu, visited by a spacecraft that returned samples from it, the drift is about 280 meters per year. Bennu has a small but non-zero chance of colliding with the Earth in the late 22nd century. And the single largest uncertainty in that calculation is not gravity, or the positions of the planets, or the mass of the asteroid. It is the Yarkovsky effect. Whether a mountain of rock hits this planet in the year 2182 depends, in a very direct and calculable way, on getting the momentum of infrared photons right. There is a rotational version too, called Yorp, in which the same asymmetric emission from an irregularly shaped body applies a torque and changes how fast it spins. That has been measured directly as well, on an asteroid so small it was named after the effect. Over long enough periods, Yorp can spin an asteroid fast enough to fling material off it, or to split it in two. A good fraction of the small binary asteroids in the solar system may exist because sunlight spun their parents apart. Which brings us to the obvious question. If light can push a mountain out of its orbit given a few million years, what could it do to something we designed on purpose to be pushed? The answer is a sail, and the reason it has to be a sail rather than an engine is the number we worked out earlier. Every newton of thrust from generated light costs 300 megawatts. You cannot afford to make the photons, but you do not have to. The sun is already producing them, in quantities beyond any reckoning, and they are already streaming past. A sail does not pay for its propellant. It only has to be large, thin, and reflective. On the 21st of May 2010, the Japanese Space Agency launched a spacecraft called Icaros, which unfurled a square membrane 20 meters across the diagonal, made of polyamide film about 7.5 micrometers thick, roughly a tenth the thickness of a human hair. Over the following weeks, tracking data showed it accelerating. The thrust was about 1/10 millinewtons, which is roughly the weight of a grain of rice. It was the first object ever to sail between planets on sunlight, and it passed Venus in December of that year. It also carried liquid crystal panels that could be switched between reflective and diffuse, letting it steer by changing the reflectivity of parts of its own sail, with no moving parts and nothing expelled. In 2019, a spacecraft called LightSail 2, paid for largely by small donations from members of the public, deployed a 32 square meter sail in Earth orbit and raised the high point of its orbit by about 2 kilometers using nothing but sunlight. In 2024, NASA flew a composite boom sail of 80 square meters as a step toward much larger structures. And there is a quieter example that I find more persuasive than any of them. The Kepler Space Telescope lost 2 of its stabilizing reaction wheels, which should have ended the mission. Engineers rescued it by balancing the telescope against solar radiation pressure, using the push of sunlight as a third gyroscope. It went on to discover hundreds more planets in that configuration, a force too small to feel, holding a telescope steady. All of that is light-moving matter across the solar system, and it is impressive, and it is also the least interesting thing this effect does. Because while astronomers were watching sunlight rearrange asteroids, a man in a laboratory in New Jersey was working out how to use the same force to pick up a living bacterium without touching it. Arthur Ashkin spent most of his career at Bell Laboratories in New Jersey, and in the mid-1960s he became interested in a question that most of his colleagues considered a curiosity at best. Could you use the momentum of light to move small objects deliberately? The laser had recently been invented, which changed the calculation entirely. A laser concentrates a great deal of optical power into a very narrow beam, and while the total push is still tiny by human standards, if the thing you are pushing is small enough, tiny is plenty. In 1970, he published a paper in Physical Review Letters describing the acceleration and trapping of micron-sized particles by radiation pressure. He had taken small transparent spheres suspended in water and found that a focused laser beam would drive them along it. That much was expected. What was not expected was the second thing he found. There are 2 distinct optical forces at work, and they behave very differently. The first is radiation pressure proper, the scattering force, and it does exactly what we have spent the night describing. It pushes the particle along the direction the light is traveling. The second is subtler. If the beam is not uniform, if it is brighter in the middle and dimmer at the edges, as a focused laser beam always is, then a transparent particle, sitting slightly off-center, experiences a force pulling it toward the bright region. This is the gradient force, and it arises because the particle refracts the light passing through it, bending the beam, and, by the same conservation argument we have been using all night, recoiling in the opposite direction. Put those 2 together, and something remarkable becomes possible. If you focus the beam tightly enough, the gradient force can exceed the scattering force, and a particle will not be pushed away, but held, sitting in the focus of the beam, trapped in 3 dimensions, suspended in space by nothing but light. Ashkin, working with Stephen Chu, John Bjorkholm, and Joseph Dziedzic, demonstrated the single-beam gradient trap in 1986. It is now called optical tweezers, and it is one of the most consequential laboratory instruments of the last half-century. In 1987, he did something that made biologists pay attention. He trapped living things, bacteria, viruses, and then individual cells, and found that with the right wavelength, chosen so the cell would not absorb much of it, the organisms survived and went on living inside the trap. He had built a pair of hands that could pick up a single bacterium, hold it, move it, and put it down, without any physical contact of any kind. What that opened up, is hard to overstate. Optical tweezers are now standard equipment in biophysics laboratories. You can attach a microscopic bead to a single molecule of DNA, hold the bead in a trap, and measure the force required to stretch the molecule. You can watch an individual motor protein walk along a filament inside a cell and measure the force it produces with each step. A few piconewtons, a few millionths of a newton, which is the scale on which the machinery of life actually operates. The mechanical properties of individual biological molecules became measurable, one at a time, because of a force that was too small for the best physicists of the 1870s to detect. Ashkin received the Nobel Prize in Physics in 2018. He was 96 years old, at that point the oldest person ever to receive one. He had retired from Bell Labs in 1992, 26 years earlier, and had simply carried on working in a laboratory he had built in the basement of his house. When journalists called on the morning of the announcement, he told them he could not talk for long because he was busy with a paper on solar energy concentration. He died in September of 2020, at 98. 55 years between the first experiments and the prize. Most of those years spent on something the field regarded as a sideline. There is a second application of light's momentum that is, if anything, even more surprising, and it runs in the opposite direction. Ashkin used light to hold things still by pushing them into a trap. It turns out you can also use light to stop things by pushing against them directly, and the things you stop are individual atoms. The idea is called laser cooling, and it was proposed independently in 1975 by Theodor Hansch and Arthur Charlot, and by David Wineland and Hans Deymelt. Here is how it works. An atom absorbs a photon of exactly the right energy, and in doing so, it takes the photon's momentum. For a sodium atom absorbing a resonant photon, that single kick changes its velocity by about 3 centimeters per second. A nudge, but a real one. A moment later, the atom re-emits a photon and recoils again, but the re-emission goes in a random direction. Do this once and nothing much happens. Do it 10 million times a second, which is what a strong resonant beam achieves, and the absorptions all push the same way, while the emissions average out to nothing. The result is a deceleration of around 1 million meters per second squared. That is 100,000 times the acceleration of gravity, applied to an atom, by light. A sodium atom coming out of a hot oven is moving at something like 1 kilometer per second. Point a laser at the beam, tuned correctly, and you can bring those atoms to a near standstill in less than 1 meter of travel and about 1,000th of a second. Roughly 30,000 photon absorptions, each one worth 3 centimeters per second, adding up. Temperature is nothing more than the random motion of particles. Stop the motion, and you have removed the temperature. Laser cooling routinely brings atomic gases down to millionths of a degree above absolute zero, and with refinements, to billionths. Stephen Chu, Claude Cohen-Tanuji, and William Phillips shared the Nobel Prize in 1997 for developing it. In 1995, it made possible the creation of Bose-Einstein condensates, in which thousands of atoms occupy a single quantum state and behave as one object. The same trick has since been turned on objects far larger than atoms. In cavity optomechanics, a small mechanical oscillator, a membrane, a mirror on a spring, a glass sphere suspended in a beam, is placed inside a laser cavity and cooled by radiation pressure until it stops vibrating almost entirely. Groups have brought such objects down to their quantum ground state, the lowest vibrational level permitted to exist, using nothing but carefully timed light. Ashkin himself had levitated glass spheres in air with an upward-pointing laser as early as 1971, balancing radiation pressure against gravity and watching them hang there. The line from that demonstration to a mechanical object held in its quantum ground state runs through exactly one idea, and it is the one we derived 2 chapters ago. And it has a consequence in your pocket. Modern atomic clocks, the ones that define the second, that keep the world's timekeeping system synchronized, that make satellite navigation possible, use laser-cooled atoms, because atoms that are nearly stationary can be interrogated for much longer and give a far sharper answer. Which means the international definition of time now depends, in a load-bearing way, on the fact that light carries momentum. 400 years from a comet tail nobody could explain, to the definition of the second. There is one last place this shows up, and it is the one I find most unsettling, because it is where the push we have been calling too small to matter becomes the thing standing in the way. Gravitational wave detectors work by bouncing an extremely powerful laser between mirrors weighing about 40 kilograms each, and measuring changes in the distance between them smaller than the width of a proton. At that level of precision, the laser is not a passive observer. The photons hitting the mirrors push on them, and because the arrival of photons is subject to quantum fluctuations, the push is not perfectly steady. It jitters randomly and shakes the mirrors. This is called quantum radiation pressure noise, and it was directly observed influencing the mirrors of a gravitational wave observatory in a result published in 2020. It sets a floor on how precisely the instrument can measure, and it cannot be removed by building better mirrors, because it is not a defect, it is the momentum of light, behaving exactly as it must. So we have arrived somewhere strange. The push that took 27 years to detect is now, in the most sensitive instruments ever built, one of the main things getting in the way. Which might make you think that at this point, everything about the momentum of light is understood down to the last decimal place. It is not, and the thing that is not understood is not exotic. It is not at the Planck scale, or inside a black hole, or in the first microsecond of the universe. It is what happens when a beam of light goes into a glass of water. Light slows down inside matter. Not the light itself, exactly. This is one of those statements that is true at the level we need and misleading if you push on it. But the effective speed at which a wave propagates through glass, or water, or diamond, is lower than its speed in vacuum. In water, light travels at about 3/4 of its vacuum speed. In ordinary glass, about 2/3. In diamond, about 40%. The ratio between the vacuum speed and the speed in the material is what we call the refractive index, and it is the reason a straw looks bent in a glass of water and the reason lenses work. So here is a very simple question. A beam of light is traveling through empty space, carrying a certain amount of momentum. It enters a block of glass. It slows down. What happens to its momentum? That question was asked in 1908. It has not been answered. I do not mean it is difficult, or that the experiments are imprecise, or that it is one of those questions that only matters at the fringes. I mean that 2 of the most capable theoretical physicists of the early 20th century derived 2 different answers, both from defensible starting points, and that both answers have been supported by careful experiments, and that the disagreement has run continuously for well over a century and is still generating papers. Hermann Minkowski, the same Minkowski who gave special relativity its geometry, derived his answer in 1908. He concluded that light entering a medium gains momentum. Its momentum is multiplied by the refractive index. Light in water, on his account, carries about 1/3 more momentum than the same light in air. Max Abraham derived his answer the following year, in 1909. He concluded the opposite. Light entering a medium loses momentum, divided by the refractive index. Light in water carries about 1/4 less. These are not close. For water, the 2 predictions differ by the square of the refractive index, a factor of about 1.77. For a high-index glass, the gap is wider still. And they do not merely differ in size. In some experimental arrangements, they predict pushes in opposite directions. So somebody should just measure it. That was, broadly, the 20th century's plan. In 1954, R.V. Jones, C.S. Richards measured the radiation pressure on a mirror immersed in a liquid and found that the pressure scaled with the refractive index of the liquid. Minkowski, Jones repeated the work with much greater precision in 1978, with the same conclusion. In 1973, Ashkin, the same Ashkin, and Joseph Dziecic focused a laser pulse onto the surface of water and watched what the surface did. If Abraham were right, the surface should be pulled inward. If Minkowski were right, pushed outward. It bulged outward. Minkowski again. But in 1975, Walker, LaHoz, and Walker suspended a dielectric disk between crossed electric and magnetic fields and measured the torque on it, and found the force that Abraham's formulation predicts. Abraham. And in 2008, a group led by Weilong Shi reported that a free-hanging silica filament recoiled inward as light left its end, again pointing to Abraham, although the interpretation of that particular experiment has been vigorously disputed ever since. So the experimental record does not adjudicate. It splits, cleanly and consistently, along a line that nobody could quite locate for decades. Let me make this concrete before we go into what the resolution might be. Imagine a block of glass, a few centimeters on a side, hanging in a vacuum chamber from a fiber so fine you cannot see it. Everything is still. There is no air, no vibration, no light, except what we are about to introduce. Now a pulse of laser light enters the block through one face, travels through it, and leaves through the other side. It is not absorbed, it is not reflected, to any degree that matters. It goes in one side and comes out the other, and the block is left exactly as it was. Same temperature, same everything. Which way does the block move? Take a moment with it. The light enters, slows down, speeds back up on exit, and continues on its way. Nothing has been taken from the beam, and yet the block must move, or must not move, in some particular way, and there is a fact of the matter about which. The honest answer is that it depends on how you divide up the momentum between the light and the glass while the light is inside, and that division is not something the theory hands you. It is something you choose when you decide where to draw the line between the field and the material it is passing through. The field nobody draws turns out to be the field nobody can cleanly separate. That is the deepest version of the problem, and it was stated clearly in a comprehensive review published in 2007 by Pfeiffer, Nieminen, Heckenberg, and Rubinstein Dunlop. Their point is that the total momentum of the whole system, light plus glass together, is completely unambiguous, and every formulation agrees on it, and every experiment is consistent with it. What is ambiguous is the accounting. How much of that total belongs to the light, and how much to the medium, is a question about bookkeeping conventions, and the theory does not contain a unique answer. In 2010, Stephen Barnett published a paper with a title that tells you what it was attempting: Resolution of the Abraham-Minkowski Dilemma. His argument is that both formulas are correct, and they are the answers to two different questions. The Abraham momentum, he argues, is the kinetic momentum, the one associated with the transport of energy, the one you want when you are asking how the center of mass of the whole system moves. The Minkowski momentum is the canonical momentum, the one conjugate to position in the formal sense, the one that appears in the de Broglie relation, the one that governs how the light diffracts and interferes inside the material. And there is good evidence for that reading. When atoms in a Bose-Einstein condensate diffract off a light grating in a medium, the momentum that shows up in the diffraction pattern is the Minkowski one. When you ask how much the whole apparatus recoils, you get the Abraham one. Different questions, different momenta, both real. That is an elegant resolution, and a great many physicists regard it as essentially settled. But it is worth being precise about what it settles. It says the two quantities are both meaningful and correspond to different physical questions. It does not answer the original question in the form it was asked. How much momentum does the light itself have inside the glass? Because that question presupposes a clean separation between the light and the glass that the physics does not provide. Inside a medium, the light and the matter are not two things sitting next to each other. The wave propagating through glass is a combined excitation of the field and the electrons in the material, moving together. Asking which of them owns the momentum is a bit like asking which half of a wave on a rope owns the motion. Papers on this are still being published. It is not a historical curiosity being politely tidied up. It is a live literature. There is a small human footnote to the disagreement that I cannot leave out. Minkowski did not live to defend his paper. He died in January of 1909 of appendicitis at the age of 44, only weeks after the work was presented. Abraham's paper appeared later that same year, arguing against a man who was already dead, and Abraham himself spent much of the rest of his career as one of the sharpest critics of Einstein's relativity, opposing it on grounds that turned out to be wrong, while being unusually good at the mathematics of electromagnetism. Max Born, who wrote his obituary in 1923, described him as loving his absolute ether, his field equations, and his rigid electron, and said that his opposition had been a valuable irritant. Two men, neither of whom was around to see the 20th century out, left behind an argument that has now outlasted both of them by a century. It also matters practically, which is worth saying, because it would be easy to file this under interesting but irrelevant. Optical tweezers usually operate in water. Designing them requires knowing how much momentum the trapping beam carries in the medium. In practice, experimentalists use whichever formulation matches the measurement they are making, which works perfectly well and is also a slightly uncomfortable way to run a science. I want to be careful here about what is and is not in doubt, because this is exactly the sort of thing that gets exaggerated. In vacuum, there is no controversy whatsoever. Momentum equals energy over the speed of light. This has been verified by Compton scattering, by radiation pressure measurements, by atomic recoil, by laser cooling, by spacecraft navigation, and by every other means anyone has devised, and it is not in question at any level. Nothing we derive tonight is threatened. The mechanism holds. The equation holds. What is unresolved is narrower and, in a way, more interesting than a broken law would be. It is a place where physics is completely certain about what will happen. Every experiment has been predicted correctly by somebody, and genuinely unclear about how to describe what is happening. The predictions are safe, the words are not. And I find that more unsettling than an outright gap in the theory, because a gap is at least honest about itself. This is a case where a question that sounds elementary, how hard does light push on a piece of glass, turns out, after 118 years of argument, to depend on a distinction the universe may simply not make. There is one more thing we have been assuming all evening, quietly, without ever examining it. Every equation we have written down, every derivation, every one of those experiments, has rested on a single input we have never questioned. We have assumed that light has no mass, and it turns out nobody has ever measured that. Zero is not a measurable quantity. That sounds like wordplay, and it is not. Every measurement has an uncertainty attached to it, and what a measurement gives you is a value plus or minus a margin. If the true value happens to be zero, the best your instrument can ever tell you is that the value is smaller than your margin. Reduce the margin, and you get a smaller number. Reduce it again, and you get a smaller one still. You never get to zero. You only ever get to smaller than we can see. So when a chart of fundamental particles lists the photon's mass as zero, that number did not come from an experiment. It came from a theory, and the experiments have only ever established a ceiling. The ceiling is very low. The particle data group, which maintains the official values, quotes a laboratory limit of about 1 × 10⁻18 electron volts. That figure comes from tests of whether the electric force really falls off exactly as the inverse square of distance, and from measurements of planetary magnetic fields, Jupiter's in particular, because a massive photon would cause a planet's magnetic field to die away with distance faster than it should, and Jupiter's field is large enough and well mapped enough to notice. To put that ceiling in proportion, an electron has a mass of about 511,000 electron volts. The photon's mass, if it has one, is at most something like a millionth of a billionth of a billionth of a billionth of an electron's. There are stronger limits still, coming from the behavior of the solar wind, which push the ceiling down by another 9 orders of magnitude, though those depend on assumptions about the plasma physics that not everyone accepts. Now, what would actually be different if the photon had mass? 3 things, mainly, and they are all things we look for. The electromagnetic force would have a finite range. Instead of falling off forever as the inverse square, it would fade away over a characteristic distance set by the mass, dying exponentially beyond it. Radio would stop working past a certain distance. Galactic magnetic fields could not extend as far as we observe them to extend. Light would have a third way of vibrating. Ordinary light has 2 polarization states, both perpendicular to the direction of travel. A massive particle would necessarily have a third, oscillating along the direction of motion. Nobody has ever detected such a state. And the speed of light would depend on its color. Higher energy light would travel slightly faster than lower energy light. This one has been tested rather beautifully, using fast radio bursts, millisecond flashes from other galaxies, billions of light years away. A pulse that brief, traveling that far, is an extraordinarily sensitive clock. Any difference in speed between the high-frequency and low-frequency parts of the burst would spread the pulse out on arrival. What is observed is consistent with them all arriving together. And there is a 4th consequence, which is conceptual rather than observational, and which I think is the most interesting of the 4. If the photon had mass, the speed of light would no longer be the speed of light. Relativity is usually taught as a theory about light, and the constant at the center of it is described as the speed light travels. That is not quite what the constant is. It is the maximum speed at which cause can reach effect, the speed limit of the universe, the rate at which influence propagates. It appears in relativity because of the structure of space-time, not because of any property of photons. We identify that limit with the speed of light for a simple reason. We assume the photon is massless, and anything massless must travel at the maximum speed. It has no choice. A massless particle cannot go slower because it has no rest frame to be slow in. Give the photon even a minuscule mass, and that identification comes apart. Light would then travel just below the universal limit, in the same way that a very light neutrino does, indistinguishably below it, but below it. There would still be a speed of causality. Nothing about relativity would break. It is just that the fastest thing we can measure would no longer be the fastest thing there is, and we would have no way of ever measuring the real limit directly, because we would have nothing that traveled at it. That is worth sitting with. The most famous constant in physics might not be a fact about light at all. Light might simply be the fastest messenger we have, standing in for something we cannot reach. There is also a strong theoretical reason to expect exactly 0. The mathematical symmetry that underpins electromagnetism in the Standard Model requires the photon to be massless, and that same symmetry is what guarantees that electric charge is conserved. Give the photon a mass, and you break the symmetry, and charge conservation becomes something you have to argue for, rather than something that comes for free. That is a good reason. It is a reason to believe. It is not a measurement. And the honest sentence is not the photon is massless. The honest sentence is, the photon's mass is smaller than anything we can detect, and our best theory says it should be exactly zero. I want to be clear that this does not undermine anything we have done tonight. Even at the very top of the allowed range, the corrections to everything we derived would be far below any conceivable experimental precision. The magnetic field would still rectify the electron's motion. Momentum would still equal energy over the speed of light, to more decimal places than anyone will ever check. Comet tails would still point away from the sun, but there is something worth noticing in the shape of it. We began tonight on an island where every dog was brown, and we found out that a rule we had taken for a law was only a habit formed by an unrepresentative sample. Then we found the mechanism and the general equation, and we watched the effect run stars and steer asteroids and hold single bacteria in mid-air. And at the end of all that, standing on much firmer ground, we find another one. The photon is massless. Everyone knows it. It is on every chart, and it is an upper bound wearing the clothes of a fact. I do not say that to unsettle you, and I certainly do not say it to suggest that physics is untrustworthy. The opposite. What makes physics trustworthy is precisely that it keeps the distinction visible, that somewhere in the literature there is a careful person maintaining the difference between the number we have measured and the number we believe, and updating the ceiling every few years, and never once quietly rounding it to zero. And so we end where we started, looking at a tail that points the wrong way. Kepler saw it in 1619 and guessed that light was pushing. He was right, and he had no way to know he was right, and it took 250 years for anyone to produce a number and another 27 to detect it. In between, the best minds available did what all of us do all the time. They took a rule that had worked everywhere they had ever looked, and assumed that everywhere they had ever looked was everywhere. The strange thing about tonight's subject, in the end, is not light. Light has been entirely consistent. It has been carrying momentum in exactly the amount its energy dictates, in every beam that has ever crossed any space, for 13.8 billion years, without exception and without apology. The strange thing is us. The strange thing is how easily a description of the neighborhood becomes a law of the universe, and how invisible that promotion is while it is happening, and how much of what any of us are certain about tonight is simply the shape of the small, slow, heavy place we happen to be standing in. Thank you for spending these hours with me, following a push too small to feel from a comet's tail, all the way down to a single atom brought to a standstill. If this kind of slow unpicking is something you value, a like or a subscribe genuinely helps this channel keep going, and it means a great deal to me. And remember, the next time sunlight falls across your hands, it is not only warming them, it is pushing. Good night, and may you never look at a beam of light the same way again.